This one starts out with a circular motion classic, a car negotiating a flat circular curve. So here I've drawn a free body diagram real quick. The car looks kind of funny, but the car is coming toward you and executing a circular turn where the radius of the circle is to the right of the car, as it's shown here in the free body diagram. The car's weight acts downward, normal force acts upward. And what I'm asked, based on the given information, is to find the net force that causes the circular motion of the car. It's strange to ask for the net force because I know the nature of the force that causes the circular motion. It's friction that makes a car go around in circular motion. So on my free body diagram, I've written the force of friction, F, but really it is the net force. Finding the answer here is as simple as calculating the mass multiplied by the centripetal acceleration. That is m times the speed squared divided by the radius. That is the net centripetal force that causes the circular motion. You have to be careful in this particular version of the problem that appears in the assignment because the diameter of the circle is given and not the radius. And it's frustrating to get tripped up by that. We know that it's the radius that appears in the equations that we use, but from time to time they try and trip us up with the diameter. This next one is really just taking the first one a bit further. Instead of a car going around a curve, this is a bicycle going around a curve. The physics is identically the same. Because just as it is the friction force that makes it possible for a car to negotiate a curve, it is the friction force that makes it possible for a bike to go around. The free body diagrams are identical. Weight downward, normal force upward, and a friction force directed towards the center of circular motion. In this problem, it is the friction force that is the centripetal force. So here I've set the friction force equal to mv squared over r, but in order to get my answer, which is what must the coefficient of friction be, I'm going to have to go a bit further. I know that the friction by definition is mu times the normal force. And so I plug that in for the friction, but I also look at my free body diagram and I know that the normal force is equal to mg. So about halfway through my solution here, I have mu mg is equal to mv squared over r. Notice that I have a mass on the left and a mass on the right, and they cancel. It's very, very common with these problems for students to read the problem statement and say, oh, well, I can't solve it because I don't know the mass. The mass is not given. Sometimes I have to persevere a bit until I get to the part of the problem where I discover that the mass cancels out. Anyway, on the left-hand side, I'm left with mu g, and on the right-hand side, v squared over r. And it turns out in the problem statement, I have everything I need now to calculate the coefficient of friction, which will be equal to the speed squared divided by mu times g. Make sure you use SI units, everything in meters, kilograms, and seconds. The next item on offer is this object that's tied to a string, and it's being whirled around in horizontal circular motion on a table. The only reason the table is there is you imagine if you take an object and you swing it around in circular motion, like just on the end of a string, it never actually gets perfectly flat. It's never a flat circular plane. So in the description of this problem, the table is there to force flatness into the thing. At any rate, I'm given an RPM, which is a number of revolutions per minute, which I talked about in a previous video where I said that if I take RPM, divide by 60, I get the frequency in hertz. The mass in this problem is given in grams, so you're going to have to convert that to kilograms by appreciating that there are 1,000 grams in 1 kilogram. Also, the radius is given in centimeters, and so you're going to want to convert that to meters. Everything in meters, kilograms, and seconds. Anyway, it's easy to calculate the speed using the equation 2 pi r times the frequency. And then I want to calculate how much tension is in the string. Well, the tension is the only force that is responsible for creating the circular motion in this case. So calculating the tension is as easy as doing mv squared over r, the centripetal force. Next up is the box on a truck. The idea here is that the truck, there's a box that's sitting in the back of a truck, I suppose like a panel truck, a delivery truck. And when the truck is motionless or moving along at constant velocity, the box just sits on the floor. And so if I were to draw a free body diagram, the weight of the box is down, the normal force is upward. But now the truck is going to go around a curve, and I suppose the box slides over to the side of the truck. But it doesn't fall off the truck because there's a wall to the container of the truck. But that wall pushes against the box. So what they want to do here is they want us to imagine what speed would the truck have to be driven such that the force that the wall exerts on the box is equal to the weight of the box. Well, that force that the wall exerts on the box is the force that is causing the circular motion of the box. That force is the centripetal force. My centripetal force law states that F is equal to mv squared over r. So all I'm going to do here is say, I want that centripetal force to be a force that is so great that it is as great as the weight of the box itself. So I've set the centripetal force equal to mg, which is equal to mv squared over r. Look, Ma, the masses cancel. Mass on the left-hand side, mass on the right-hand side, and I'm left with g is equal to v squared over r. And I can easily solve for the speed of the truck that would cause this to happen. The assignment finishes up with this elaborate problem involving a dog sort of wriggling, twisting about in order to shake water off the fur. And it describes how the cohesive forces of the water keep it going in circular motion on the fur, but there's a limit to those forces, and then the water droplets fly off. So it's a very elaborate thing, and I actually wrote a slide for it, but I lost it somehow in this process. Anyway, for all of its elaborate description, is a very, very simple problem to solve. We simply have to appreciate that the force required to create circular motion is equal to mv squared over r. And in the dog problem, you have all of those things. So you just go ahead and plug in with appropriate units. I think maybe the droplet is measured in milligrams, thousandth of a gram. But anyway, you get your units right, everything will work out great. Mm-hmm.